Okay, so this point is about this problem is about a point that traverses basically half a circle. Okay, so let's go through the problem. A point traversed half a circle of radius r during the time interval. So basically the radius of the circle and the um, time taken to traverse half the circle is basically given. So we have to calculate the following quantities that are basically averaged over time. The mean velocity v. Okay, so here is a catch. So this is something this is something that is present in Irodov, which is wherever you do not have the this is v. Basically this is v, which is not in bold, which means it's not a vector. So it basically translates to the average speed, since it's not a vector, sign is not present. Whereas the second part, the modulus of the mean velocity vector, it's very clearly written as the mean velocity vector, the magnitude of that. So this is clearly average velocity magnitude, of course, average velocity magnitude. This is something that is a catch over here, since I'm just repeating this over here in the first part. Since there is no vector symbol, it is average speed. In the second part, since there is a vector, which is written wherever anything is mentioned in bold, it basically represents a vector in the Irodov book. So this is basically the average velocity's magnitude. C part is the modulus, or okay, another thing is the modulus means the magnitude. So modulus of the mean vector, again, of the total acceleration. This is essentially again the average acceleration, right? So we need to find out first the average speed, the average velocity magnitude, and the average acceleration. Of course, the magnitude. For this tau equal to 10 seconds, for which the point basically traverses the half circle. Now, okay, acha, one more thing, if the point is moving with constant tangent acceleration, okay, what that means is, let's draw it. So let's assume that this is a circle and that it's, sorry, I'll redraw certain. Okay, so is a circle whose radius is given to be capital R. Okay, now let's say it goes from point A to a diametrically opposite point B along the circle, which means that it has traversed half the circle, right? Okay, so whenever it is saying traversed half a circle, it means that it is going in the, like, going in the, or through, on the perimeter of the circle, and it goes to the diametrically opposite point, then only it is covering half the circle. Okay, now, okay, so first of all, A, the mean velocity. So I will calculate everything in terms of tau and capital R. You can substitute the values and get the, the final value in terms of centimeters per second over here. I'll just do it in terms of the variables. So the mean velocity, I'll retain the symbols, which is, okay, the mean, actually I should call it the average speed, sorry for that. The average speed is basically the total distance divided by the time taken. Okay, so the distance, so this distance basically half the circumference. So half the circumference is 2 pi capital R divided by time taken is tau. 2 cancels, it becomes pi R, sorry, it becomes pi R by tau. Okay, you can substitute the values to get the value, final answers value. Second is modulus of the mean velocity, is the average velocity magnitude, which is, whenever I put bar, this means it is a vector, right? And that is replaced in Irodov's book by the bold, by making the character bold. So this is nothing but the total displacement divided by the time taken. So displacement over here is basically the AB. So this is basically your displacement. Let's call it S. This is your S, which is AB. So basically AB by tau. What is AB? AB is nothing but the diameter. Diameter is 2 times radius. So 2 times radius, sorry, 2 times radius divided by tau. Okay. Now C part is average acceleration magnitude. Okay, so is represented by this. It is basically, so the average acceleration is basically the change in, or rather I should say, to be more clearer, magnitude of change in the velocity vector. So it's the magnitude of change in the velocity vector. So it's basically change in the velocity vector, whatever you'll get finally, basically the final velocity vector minus initial velocity vector. That also will be a vector. So the magnitude of that, okay, divided by the time taken is basically your average acceleration magnitude. Okay. So if I just write it in terms of, let's say final velocity is represented by Vf and the initial velocity is represented by Vi, then I can write it as modulus or magnitude of Vf minus Vi divided by the time taken is tau, right? Okay, so now for this part of the problem, for the third part of the problem, this thing is really important. So it has a constant tangential, sorry, so it has a constant tangential acceleration. So what does that mean? So what it means is, so like the particle is always accelerated along the instantaneous tangent. So when it is here, let's say, the acceleration direction is this way. When it is here, the acceleration direction is here. Okay, so you can consider it this way, that from A to B, even if the path is curved, the acceleration is always along the direction of its immediate velocity, because velocity is also tangential, the acceleration is also tangential. Okay, so the velocity and the acceleration, right, are in the same direction, right? We all since, I'll just write this, since velocity and acceleration are in the same direction, that is tangential at all times, we can apply this equation, right? We can apply the magnitude of Vf is equal to magnitude of Vi. Magnitude is important here, right? Because the direction is changing, but we are only considering the, at every point it is tangential. Of course the direction is changing, the tangential direction is changing, but it is always tangential. So Vf is equal to Vi plus, we can apply this kinematics equation, plus A, let's say it is called AT for A tangential, into tau, let's say. This is the thing. Okay, now one more thing that is really important to understand. I'll redraw this trajectory from A to B, right? From A to B, if we consider the velocity directions initially and finally, so this is basically your Vi and this is basically your Vf. They are in opposing directions. So what we can say is, when you are doing this is essentially, because these are vectors in opposite directions, when you subtract, so whenever you subtract like vf, okay, so if, whenever you subtract vi from that, you are basically adding vi in the opposite direction, right? Subtracting a vector is basically adding it in the opposite direction. So when you subtract, you are basically adding the two in this case. Yeah, the vi minus vi is in the same direction as vf. So basically what you're doing is you're adding up. Basically you are adding up the two when it comes to magnitudes. All right. So I'll just so see, this is same as writing vf is equal to vi, say t tau. It's like basically this represents the magnitude itself. All right. So also we know that along this circular path, we can say that, okay, the circular path is equal to vi tau plus half at tau square, right? We can say that, right? Because exactly because of this relation written in red, this velocity and acceleration basically aligning at all times. So now circular path, the basically it is nothing but half the circumference, which is pi r. Okay, it is vi tau plus half at tau square. Okay, what we need to find out, we need to find out vf, this thing vf plus vi by tau. Now we can write at in terms of vf and vi, right? This becomes vi tau plus half at is nothing but vf minus vi by tau. At is nothing but vf minus vi by tau into tau square, right? This cancels out. So this becomes so if you see it is nothing but vi tau plus vf tau by 2 minus vi tau by 2. You can group the first and third terms essentially, and you can take tau by 2 common, or tau common rather. Vi plus vf divided by tau square by 2 times vi plus vf by tau. This is tau square by 2 into mod, right? So is pi r. Hence average acceleration magnitude equals 2 pi r divided by tau square, the required value, 2 pi r by tau square. You can substitute the values and get the answer's value.